first things I want to do is to make sure that it's kind of clear that the coiling of the shell in gastropods is a completely separate phenomenon from torsion. Okay, so coils or whorls in the shell is not the same thing as torsion. So in fact, let's talk a little bit about that first, and then I'll come back to torsion. In the gastropod shell, and as you've probably known just from collecting seashells for most of your life and looking at the ones in lab, that there's an incredible diversity of shell styles and sizes and shapes and forms. And this coiling does tend to be one thing that's relatively consistent throughout different kinds of gastropods here. And so there's some terminology, of course, every turn is called a whorl. There's the apex of the shell, which is just the top point. The spire tends to be at the top. Oops. And then here you can see the operculum is closed. I don't know why my computer wants to keep going forward without me. The operculum is closing off the aperture of the shell here. When you take a look at a cross section, you can see this column or columella inside the shell. So a little bit of structure there. One of the things that happens as a consequence of the whirling of the shell is that in some gastropods, the twirls or the whorls are actually on a single plane, and so they call that planispiral. Okay, if you were to draw the sort of coil and leave it in a single plane, it might look like this right here. And then if you were to pull that out and go upward, then suddenly you've pulled the whorls out so that you've got this little bit more of a cone shape. So what happens is that the snail tends to be heavier on one side than the other. Often it's the right side, and I'm going to talk about this right-left thing in a minute. Sometimes it's the left side. So because suddenly they're heavier on one side, they have to sort of angle their body back towards the other side to hold the center of gravity over the middle part of the body. And so what you'll see is that when you look at a gastropod, and again, take a look at the live ones that we've had in class, especially those small ones, as they're walking, and you'll see that the shell is tilted at an angle so that the weight can be centered over the middle of the body. What this slide here is showing is the fact that some, don't know why that's happening, while some gastropod shells are right-handed, or what it was called dextral. So basically, if you hold a shell facing you and the opening is on the right side, it's dextral. And if you look down here, if you hold the shell and it's facing you, then the opening is on the left side, and that's called left-handed or sinestral. And this term sinestral actually comes from the word sinister. Of course, being left-handed was thought to be a sinister or bad thing. No offense to all you left-handed people, but that was the way that people were often thought of as being evil or from the devil or something if they were left-handed instead of right-handed, which is why a lot of kids were forced to be right-handed in the old days. Unfortunately, that sort of demonization of left-handed people doesn't happen anymore. But anyway, the word sinestral kind of comes from that. So dextral and sinestral. And this is kind of showing if you were to take a shell on a single plane and pull the whorls through to the bottom and then flip it over, you get the sinestral instead of the dextral. Anyway, not a major point, but a little bit about how the shell is angled helps us to understand a little bit how why they hold their bodies. So let's come back to the concept of torsion. And one of the first things that I want to say, and that I want you to remember, is that torsion happens in the larval stage. Okay? Now this diagram here is showing torsion as if it may be happening in an adult, but it doesn't happen in the adult, it happens during development. Okay, so as the animal is developing, this phenomena called torsion happens in the larvae. Okay, and in fact, the picture in your textbook shows it happening in the larvae and then in this so-called hypothetical adult. So this is showing it as if it were going to happen in an adult. So one of the things that you'll notice here is that there's a lot of labeling going on in this diagram, and you don't need to really pay attention to most of it. If you take a look at the ctenidia, remember we have a left and right ctenidia, those are the gills. We have the mouth, the anterior end, the anus. So follow the digestive tract here from mouth to anus. And then the other thing to look at are these nerves over here. Okay, so there are different names for these nerves, and you don't need to remember that they're called pleurointestinal connective nerves or whatever they're called. Just follow these little lines. Okay, and basically if you just follow the movement of the digestive tract, and again, this is something that's occurring during development, but it's as if you were to take a snail, all right, and its digestive tract was straight, and that if you held the foot and head in place, but took your hand and held the visceral mass and turned it 180 degrees. Okay, notice that we're just going to twist, 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 turn this 180 degrees. So now these ctenidia here are kind of on a 90 degree, and then they're coming around closer to the front, right? And now our digestive tract is pretty coiled, and by the time we're done here, the ctenidia are facing completely anterior. The digestive tube has taken a complete U-turn, and now these connective nerves have crossed over. So you can see the results of the process of torsion, again, which occurs in the larval phase, and we're seeing it here in the adult. So the consequences of torsion, again, is that now you've got the anus lying on top of the mouth, and you think, well, how could that be good? You got waste material exiting the digestive tract right over the mantle cavity. And remember that I said the mantle cavity is where water's coming in, the osphradium is there, and so aren't you going to have kind of an unsanitary condition if you've got waste material moving over the mouth? One of the hypotheses that was held for a long time, somebody kind of proposed it, and then, like many theories, wasn't tested forever. Like people said, oh, that makes sense. We don't need to bother doing experiments, which is what sometimes scientists do, unfortunately. And so it wasn't until the 80s that somebody actually tested the idea that the reason for torsion, especially in the larval stage, is that the larvae are perhaps more subject to higher rates of predation or predatory pressure. And so by having the mantle cavity in front of you instead of behind you, you can actually sense what's coming as you're moving through the environment. And if you can tell what's in front of you and what's happening, you can sense what's there, close up into your shell more quickly, and actually avoid predation. And apparently, when they've done tests of predation rates on larval gastropods in an untorted, pre-torted state, a partially torted state, that they don't seem to have any higher rates. And in fact, sometimes the torted ones have higher rates of predation than the untorted ones. So, so much for great theories. And again, there's a section in your textbook that sort of discusses some of the limitations of the experiment, where they only looked at the 90-degree turn instead of the 180. Not exactly sure why they did it that way, but anyway, the jury's still sort of out on the purpose of torsion. One of the things is that it may be that there are some advantages to the larvae, and then the adult is just kind of stuck with it. And that it may also be that torsion is something that's happened for reasons that existed in the past. And again, we talked a lot about this when I teach about evolution in some of my other classes, that just because something exists doesn't mean that it has a positive adaptive significance. Sometimes, as long as the pros of other situations outweigh the cons, then you'll see something maintained through evolutionary time. And we could be looking just at a phenomena like that. There may be other things that outweigh the disadvantages of torsion that haven't really been uncovered yet, if that makes sense. We can talk more about that in class if that doesn't really make sense. And that the idea that you might have advantages in the larval and not in the adult is something that's been taken up. So, say la vie, the existence of torsion. Oh, one of the other things I was going to say is that actually the fact that in several groups there is a reduction or absence of torsion, or even something called detorsion. So the animals either don't do this torsion thing at all during development, or that they tort and then untort again. So now remember, we've got the 3 subclasses of gastropods, and it's primarily in the prosobranchs where we see torsion. But then remember those epistobranchs, those beautiful nudibranchs, mostly those guys don't exhibit any torsion. Okay, and the same is true for many of the pulmonates. So the loss of torsion, the reduction or the detorsion, is further evidence that this phenomena evolved in some groups, other groups were stuck with it, and then we see an evolutionary reversal there. So kind of an interesting thing. Okay, let's talk a little bit more about the pulmonates. Again, those were the terrestrial snails. And talking a bit about respiration, because we're going to come back to talking about respiration in the prosobranchs, or the marine aquatic snails. And remember, pulmonata kind of refers to lung. There's a few other things structurally about the pulmonates that are a bit different. You know, they tend to have eyes on these eye stalks. You don't have a siphon. We don't really have the mantle coming out from under the shell here. You just kind of have the head sticking out, a big muscular foot. This shows a little diversity of pulmonates. So here's the coiled shell. Here we have a shell more on a single plane, like that planospiral shell. And here we have slugs, which are shellless pulmonates. So the pulmonates include both the land slugs as well as terrestrial snails. And in some of the slugs, there's a reduced external shell, this little one here. And in other slugs, like some of the common limax, there's no external shell at all, but they might have a small internal shell that you can't really see in this picture. All right, so all of those things are possible with respect to the shell. One of the structures that's important that pulmonates have is this thing called a pneumostome. And remember, the prefix here, pneumo, referring to lung, stome, referring to like mouth or opening. So these guys basically have these little holes in their body. You can see it's sort of pictured there. You can see the pneumostome in this one here. The pneumostome isn't really so well illustrated over here, but basically you see a hole that air is going to go internally into their bodies. And thought maybe I had a better picture here. Somewhere I did. And so what you're going to have is you're going to have oxygen CO2 exchange from that air across some moist internalized respiratory structures. And they don't really have ctenidia. You're not going to see these folds or gill structures like you see in the marine snails. Basically, you just have a lung, which is an opening or a cavity inside the body. Okay.